Welcome to the Discrete Universe podcast.
Hello.
Today we're diving deep into two really fascinating frameworks. They challenge or maybe expand our view of gravity, especially where general relativity seems to hit some roadblocks.
That's right. We're talking about Modified Newtonian Dynamics, MOND, and Quantum-Geometry Dynamics, or QGD.
Yeah, two very different takes. And we've got a range of sources here, from reviews on loop quantum gravity, which has some links to QGD, to papers really detailing MOND's successes and failures, and the basic ideas behind QGD itself.
Our mission, really, is to unpack these ideas, look at MOND, look at QGD, see where they might overlap or where they just completely diverge in how they describe gravity.
And think about what they mean for cosmology, particularly for you, our listener, who likely has a physics background and is maybe looking for alternative ways to think about these big questions.
Okay, so MOND, let's start there. Where did it come from? Well, empirically, observations.
Right. Astronomers kept seeing this mismatch in galaxies. You calculate the mass needed to explain how fast things are spinning,
Especially stars way out in the spiral arms.
and it just doesn't line up with the mass you can actually see.
Yeah.
Stars, gas, dust.
Exactly. Those flat rotation curves. They should be dropping off according to Newton, but they don't. They stay flat.
Which is the classic argument for dark matter, right?
Yeah.
Lots of invisible stuff providing the extra gravity.
Traditionally, yes. But Mordechai Milgram came along and said, well, hold on. What if it's not missing matter? What if gravity itself acts differently when accelerations are incredibly small?
And that's the core of MOND, this idea of a critical acceleration scale. It's tiny, something like 10 tangents.
Tiny, yes. And below this, Milgram proposed that the effective gravitational pull doesn't follow Newton's inverse square law quite the same way. It changes.
It approaches where is what you'd expect from Newton. So it introduces this fundamental acceleration scale right into the physics.
And what's really compelling, initially at least, is how well this simple-sounding modification works at the galactic scale. It just explains those flat rotation curves without needing dark matter.
It's not just the curves, though, is it? There are other successes.
Oh, definitely. MOND naturally predicts the Tully-Fisher relation, this observed link between a spiral galaxy's brightness, essentially its visible mass, and the fourth power of its rotation speed, m propto v4.
Which just pops out of MOND's equations, whereas in the standard dark matter picture, you need some complex modeling of galaxy formation to maybe get it.
Right, and things like the Freeman and Fish laws relating to surface density in galaxies also seem to align pretty well with MOND predictions. So phenomenologically at the galaxy level, it's, well, surprisingly successful.
So MOND basically says, maybe all that evidence we point to for dark matter, maybe it's actually evidence that we've got gravity wrong in these very specific low acceleration situations.
That's the argument. It directly challenges the dark matter paradigm.
But okay, galaxies are one thing. What about bigger scales? The whole universe, cosmology. That seems to be where MOND runs into more difficulties.
It does. To fit observations like the cosmic microwave background, the CMB MOND cosmology generally still needs something like a large cosmological constant, similar to the standard lambda CDM model.
So it doesn't get rid of dark energy necessarily?
Not necessarily, no. And there are other potential tensions. Some studies suggest that fitting the CMD and MNND might predict, say, a different frequency of gravitational lensing by quasars than what's observed. It gets complicated.
And there's the whole issue of making MND work with Einstein, right? Finding a relativistic version.
Exactly. That's a huge hurdle. MOND, in its basic form, is a modification of Newtonian gravity. We need a theory that blends MOND with general relativity to handle strong gravity, black holes, cosmology properly.
People have tried, right? Theories like Thieves tensor vector scalar gravity.
Yes, Thieves was a prominent attempt. But these relativistic MOND theories have faced their own challenges, both theoretical, like potential instabilities or issues with gravitational wave speeds, and observational constraints. It's proven really tough to build a fully consistent and problem-free relativistic version.
And one more thing about MOND before we shift gears. That acceleration scale, mentioned it's tiny. Isn't there this weird coincidence? It's numerically quite close to C806, where C is light speed and the Hubble constant, measuring the universe's expansion.
Ah, yes. That coincidence. It's very intriguing. Is it just numbers lining up by chance, or does it hint at something deeper?
But like some connection between local physics, these tiny accelerations, and the cosmos as a whole, maybe something holographic.
People definitely speculate about that. It's one of those tantalizing hints that maybe gravity, cosmology, and fundamental physics are linked in ways we haven't grasped yet. But yeah, still very much speculation.
Okay, so MOD modifies existing laws within our usual picture of spacetime. Let's now turn to quantum geometry dynamics, QGD. This seems radically different.
Radically different is a good way to put it. QGD starts from scratch, almost. It's an axiomatic approach, trying to define fundamental aspects of reality that are invariant.
Axiomatic. So starting with basic postulates, what are they?
Well, it postulates fundamental particles called preons, positive preons and negative preons, and crucially, it proposes that space isn't a continuous backdrop.
Not continuous, so discrete.
Exactly. QGD suggests space itself is formed by a lattice or structure of these preons, and movement isn't smooth either. It happens in discrete steps called preonic leaps.
Wow. Okay, so quantized space. And these leaps, how fast are they?
The rate of these leaps is fundamentally linked to the speed of light. In QGD isn't just a speed limit in space, it emerges from the fundamental tick rate of these discrete spatial interactions.
So space is granular, made of preons, and movement is step-by-step tied to c.
How does gravity fit into this preonic world? Gravity in QGD is described through interactions involving the preons. There's talk of n gravity and p gravity, mediated by the exchange or absorption of these plus preons. It's framed in terms of fundamental momentum transfer.
Momentum transfer.
Okay.
Okay. And does this lead to an acceleration like we expect from gravity?
Yes. QGD derives gravitational acceleration from these preonic interactions and the discrete space structure. And interestingly, the result isn't always identical to Newton's law.
Ah, so like MOND, it suggests deviations maybe, particularly where?
Particularly at very small scales or potentially under very low accelerations echoing that regime where MOND also proposes changes. But QGD gets there from a completely different underlying quantum structure.
That's a fascinating. Two paths leading to potentially similar phenomena in certain regimes, but starting from vastly different assumptions about reality. One modifies classical laws, the other rebuilds spacetime from quantum bits.
Precisely. And QGD also offers an explanation for the weak equivalence principle, why gravitational and inertial mass seem the same. It argues this arises naturally from the fundamental way momentum is transferred in these preonic interactions.
Okay, and what about the big picture? Cosmology in QGD?
QGD proposes a very different early universe, a preonic universe phase, and perhaps most dramatically, it suggests that gravity, mediated by these preons, can actually become repulsive at cosmological distances.
Repulsive gravity.
Yes, due to the interplay of n gravity and p gravity over vast scales. QGD suggests this intrinsic repulsion could be what's driving the accelerated expansion of the universe.
So, an alternative to dark energy, potentially.
Yeah.
Built into the theory of gravity itself.
That's the implication, yes. A mechanism arising from the fundamental structure rather than an added component like dark energy.
What about black holes? They're usually points of infinite density, singularities, in general relativity.
Yeah.
How does QGD handle those?
Well, QGD argues that true physical singularities, like infinite density, simply can't exist because space itself is discrete. There's a smallest unit.
Like pixels on a screen, you can't zoom in infinitely.
Exactly. So in QGD, a black hole isn't a singularity. It's more like a region where matter and even photons break down into their constituent preons and neutrinos. Extremely dense, but finite.
And can things get out?
QGD suggests these preonic black holes might actually emit preons. And it makes an interesting connection, suggesting that intense fields of these emitted preons might be what we observe as magnetic fields around such objects.
Preons and magnetism. Interesting link. And this rejection of singularities, that's a general feature of QGD.
Yes, it stems from the fundamental discreteness. Infinite densities, zero volumes. These concepts don't fit within a framework built on indivisible units of space and interaction. The smooth space-time continuum we perceive is seen as an emergent property, an approximation that works well at larger scales.
Like classical physics emerging from quantum mechanics. And QGD also touches on things like redshift and energy mass equivalence.
It does. It offers mechanisms for both Doppler and potentially intrinsic redshifts based on momentum transfer to atomic electrons during photon interactions. And it provides its own foundational take on EMC, relating energy to the orientation of plus preons and linking energy conservation to their net balance.
Okay, we've got these two quite different frameworks on the table now. Let's try to crystallize the comparison for you, the listener. MOND versus QGD.
All right, fundamentally, MOND modifies Newtonian-Einsteinian gravity within a continuous spacetime. QGD rebuilds reality on a discrete quantum geometrical foundation.
The role of acceleration. absolutely central in MOND, with the key parameter triggering new behavior. In QGD, acceleration is derived from deeper preonic physics.
Cosmology. MOND struggles to provide a complete, universally accepted cosmological model without issues. QGD offers a radical alternative cosmology with repulsive gravity potentially explaining cosmic acceleration.
Dark matter. MOND is explicitly an alternative to dark matter. QGD, through its inherent dynamics, also doesn't seem to require dark matter to explain things like galaxy rotation.
And the quantum connection. QGD is fundamentally quantum from the ground up, based on discrete units. MOND is primarily classical, though people search for quantum roots, maybe linked to that approx CH0 thing.
So wrapping up our dive, MOND and QGD, two really thought-provoking ways to tackle gravity's mysteries.
MOND gives us this compelling empirical fit for galaxies, making you seriously question if dark matter is the only answer, by suggesting gravity itself changes at low accelerations. Simple idea, powerful results, but with bigger scale challenges.
While QGD, well, it's a complete rethink. Discrete space, preons, gravity, emerging from fundamental quantum interactions. It offers potential explanations for dark energy and avoids singularities, but is a much bigger theoretical leap.
Both really highlight that the story of gravity is likely far from over. From the tiniest scales to the entire cosmos, there are still deep questions.
Which leaves us, and you, pondering. Could MOND be extended successfully into a full relativistic cosmological theory? What definitive testable predictions could QGD make to distinguish itself?
And how might either of these approaches, if they hold some truth, reshape our whole understanding of dark energy, black holes, maybe even the fabric of spacetime itself?
Thank you for joining us on this deep dive. We really encourage you to look into the sources and keep thinking about these frontiers.
Yeah, what strikes you as the most compelling part of either MOND or QGD? And what do you see as the biggest hurdles each one faces? We genuinely love to know your perspective.